There are places where the laws of physics stop working. This is the strange frontier of the quantum fabric of space-time, a realm where our most trusted rules of reality break down completely. Renowned physicist John Wheeler once described a cosmic dance where space-time tells matter how to move and matter tells space-time how to curve. But what happens when that elegant dance falls into chaos? By the end of this journey, you will understand how the very foundations of our universe might be an illusion. We will venture into black holes where time itself shatters and explore the subatomic foam from which everything may be woven. What does it truly mean for the rules of reality to fail? For centuries, the universe operated like a perfect, predictable machine. Isaac Newton gave us a set of rules that described this cosmic clockwork with incredible precision. His laws of motion and gravity could tell us exactly how a planet would orbit the sun, or how an apple would fall from a tree. This entire system was built on a simple, comforting idea that space and time were absolute and unchanging. They formed a fixed, rigid stage, and everything in the cosmos was merely a player acting out its part upon it. This was the classical universe, a realm of order and certainty. Then came Albert Einstein, who radically transformed this stage. He proposed that space and time were not separate and absolute, but were instead woven together into a single, dynamic fabric, space-time. In this new view, mass and energy do not simply move across this fabric, they actually bend and curve it. Think of a taut rubber sheet. If you place a heavy bowling ball in its center, it creates a deep dimple. Now roll a marble across that sheet, and its path will curve, not because a mysterious force is pulling it, but because it is simply following the contour of the curved surface. This is the essence of Einstein's general relativity, where the sun warps the space around it and Earth rolls along that curvature, an effect we perceive as gravity. This elegant model explained the cosmos on a grand scale with breathtaking accuracy, from the bending of starlight to the precise orbit of Mercury. Yet for all its power, this beautiful classical picture is incomplete. It works flawlessly for planets and galaxies, but it contains a hidden flaw, a whisper that this smooth fabric might be an illusion, concealing a far stranger and more chaotic truth beneath its surface. Yet Einstein's grand stage of space-time was not the only revolution. While he was mapping the cosmos, another, stranger world was being uncovered in the laboratory. This was the quantum realm, a domain where the comforting certainties of the classical world dissolved into a fog of probability. The universe, it turned out, was not a perfect machine at its core, but a game of chance. Here, particles do not follow neat, predictable paths. An electron is not a tiny marble orbiting a nucleus. It is a cloud of potential, a set of probable locations where it might be found if you look for it. This is the principle of superposition, where a particle can literally be in multiple places or exist in multiple states all at the same time. It only settles into a single, definite reality at the very moment it is observed. This bizarre behavior was captured perfectly in the famous double-slit experiment. When you fire a stream of particles at a barrier with two slits, they do not simply go through one opening or the other like bullets. Instead, they behave as if they are waves, passing through both slits simultaneously and creating an interference pattern on the detector behind them. A pattern of stripes that could only form if each individual particle was interacting with itself. The act of measuring which slit the particle goes through destroys this wave-like behavior, forcing it to act like a single, localized particle. It is as if reality itself remains undecided, a shimmering set of possibilities, until a conscious observation forces it to make a choice. This inherent weirdness is not a flaw in our theories, it is a fundamental property of nature. The pioneers of quantum mechanics, figures like Niels Bohr and Werner Heisenberg, were forced to accept that the universe at its most basic level is governed by uncertainty and probability, not certainty and force. Heisenberg's uncertainty principle states that you can never simultaneously know both the exact position and the exact momentum of a particle. The more you pin down one, the more the other becomes a blur. This is not a limitation of our microscopes, it is a law of reality. The solid, deterministic world we experience is merely an average, a statistical illusion that emerges from countless quantum uncertainties. This creates a profound conflict, a schism at the heart of physics. Einstein's general relativity paints a beautiful, smooth, and continuous picture of space-time, a cosmic canvas. But quantum mechanics reveals a frantic, probabilistic, and granular reality beneath it. One theory rules the very large, the other the very small, and they are utterly incompatible. The smooth fabric of space-time, the very foundation of Einstein's universe, cannot coexist with the chaotic quantum frenzy that must be weaving it. So where does that leave us when our two most powerful descriptions of reality are at war with each other? This is the great clash, a battle between two kingdoms of physics that cannot both be entirely true. One kingdom, general relativity, governs the vast cosmic arena. It describes a universe of breathtaking elegance where space and time form a single, smooth, and continuous fabric, warped by mass and energy into gentle curves. The other kingdom, quantum mechanics, rules the infinitesimally small. Its domain is a frantic and fuzzy realm of probability, where particles pop in and out of existence and definite locations are replaced by clouds of possibility. These are not just two different theories, they are two different versions of reality, and they speak entirely different languages. The conflict is fundamental. General relativity is rigidly deterministic. If you know the initial conditions of the universe, you can, in theory, calculate its entire future. But quantum mechanics is built on chance. It states that the universe is inherently probabilistic at its core. Where Einstein's theory sees a seamless geometric fabric, quantum theory insists that energy must come in tiny, jittery, discrete packets. This is not a minor philosophical disagreement. It is a direct collision of first principles. We feel the tremors of this war most acutely in the most extreme environments imaginable. At the very center of a black hole, a place known as a singularity, the smooth fabric of space-time is predicted to curve into an infinitely dense point. At the moment of the Big Bang, the entire universe is thought to have erupted from such a point. In these realms, the vast scale of gravity meets the tiny scale of quantum effects, and our equations simply blow up, yielding nonsensical answers of infinity. The great Stephen Hawking dedicated his life to this frontier, searching for a theory of quantum gravity that could bridge the divide. He showed that black holes are not completely black but slowly evaporate, a quantum effect acting on a gravitational object, a tantalizing hint that a connection must exist. This unresolved tension is the most pressing problem in fundamental physics. It is a glaring sign that our understanding is incomplete, forcing us to look for the cracks in reality itself, the places where the laws we trust simply break down. Deep within a black hole where gravity has won its ultimate victory lies the singularity. This is the final destination, a point where the entire mass of a collapsed star is crushed into a volume of zero size. According to the equations of general relativity, the curvature of space-time here becomes infinite. The very concepts of distance and duration, the foundations of our reality, dissolve into nonsense. It is a mathematical ghost, a place where the universe's rulebook is torn to shreds. Approaching this point, calculations for density and temperature skyrocket towards infinity, a value that has no physical meaning. In physics, an infinity is not an answer, it is an error message. It is like asking a calculator to divide by zero. The system simply cannot process the request. The calculator does not give you an infinite number, it gives you an error because the operation is undefined within its logical framework. The singularity is the universe's own division by zero. Renowned physicist Kip Thorne describes these points as the boundaries of space-time itself, the final edge of the map where our understanding hits a hard, impenetrable wall. This is not a minor glitch, it is a catastrophic failure of our most powerful classical theory. The singularity is a screaming clue that we are missing a fundamental piece of the puzzle, a piece that must come from the quantum world. It is the most dramatic cry for help from physics, compelling us to find a new theory that can marry the immense force of gravity with the frantic jitter of the quantum realm. To escape the infinite fury of a singularity, we must journey in the opposite direction, shrinking down to the very smallest possible size. This is the Planck scale, a realm so tiny it defies human comprehension. The Planck length is about 1/10,000,000th of a trillionth of the diameter of a single atomic nucleus. At this unimaginable scale, the smooth, classical fabric of space-time predicted by Einstein completely unravels. The serene, geometric stage dissolves into a seething, chaotic frenzy known as quantum foam. Picture the surface of a boiling pot, with bubbles constantly forming and popping. Now, instead of water, imagine that the very substance of space and time is bubbling. In this frantic sea, microscopic wormholes blink into existence only to vanish a moment later. Entire baby universes may be born and die in an instant. This is not empty space, it is a vibrant, tumultuous arena where the gravitational field itself undergoes violent quantum fluctuations. The energy of these fluctuations is so immense that they warp the geometry of reality on the spot. This scale is named for Max Planck, the physicist who first realized that constants like the speed of light and the strength of gravity could be combined to define the universe's natural units, the absolute smallest measurements that have any physical meaning. The Planck length represents a fundamental limit to reality itself. To probe any smaller than this, you would need to concentrate so much energy into such a tiny point that you would inevitably create a microscopic black hole, instantly swallowing your experiment and any hope of a measurement. At this frontier, our everyday concepts begin to shatter. The clear sequence of cause and effect, the very idea of before and after, may become blurred and lose all meaning. Geometry itself might be granular, composed of indivisible units of space, much like a digital image is made of discrete pixels. This turbulent, foamy foundation suggests a profound idea that the smooth, continuous space-time we move through is not fundamental. It is an illusion, an average that emerges from the frantic dance of countless quantum grains, just as the smooth surface of a pond emerges from the chaotic motion of trillions of water molecules. The universe we perceive is a calm, classical ocean resting atop a quantum storm. Yet the quantum foam is not the only place where reality frays. At the edge of a black hole, a different kind of boundary exists, one that is both a final farewell and a profound mystery. This is the event horizon, the point of no return. It is not a solid wall you could touch, but a ghostly sphere in space, a mathematical threshold where the black hole's gravitational pull becomes so overwhelming that the escape velocity exceeds the speed of light. From our perspective, watching from a safe distance, a star or an astronaut falling toward this horizon would appear to behave in the strangest ways. They would seem to slow down, freezing in place just as they reached the boundary. Their light would stretch and redden, dimming into invisibility as time for them grinds to a near halt relative to us. It is as if the universe itself is projecting a frozen, fading image for all eternity. But what would it be like for the astronaut on that one-way trip? According to Einstein's general relativity, crossing the event horizon would be an utterly uneventful experience. There is no signpost, no sudden jolt, no dramatic tearing. The horizon is a mathematically smooth boundary, and the astronaut would simply float right through it, noticing nothing special at that fatal moment. Yet this is where the paradox begins. When we introduce the rules of quantum mechanics, this placid boundary becomes a cosmic crisis zone. Quantum theory insists that information can never be truly destroyed. If you burn a book, every single letter and word is, in principle, still encoded in the smoke and ashes, even if it is impossibly difficult to reconstruct. But if you throw that same book into a black hole, what happens to its information? According to classical gravity, it is lost forever, crushed into the singularity, erased from our universe. This creates the infamous black hole information paradox, a direct conflict between the foundational rules of quantum physics and the predictions of general relativity. The event horizon is not just a point of no return for matter. It is the very line where our two greatest theories of reality wage war, forcing us to question if information, the most fundamental currency of the cosmos, can simply vanish, or if the horizon itself holds a secret we have yet to uncover. This quantum whisper from the event horizon is known as Hawking radiation. The empty space surrounding a black hole is not truly empty. Quantum field theory tells us that the vacuum of space is a turbulent sea of energy, a place where pairs of virtual particles and antiparticles constantly flicker into existence. For the briefest moment allowed by the uncertainty principle, these ghostly pairs borrow energy from the void, only to collide and annihilate an instant later, repaying their debt and vanishing without a trace. Stephen Hawking's great revelation was to ask what happens when this quantum dance plays out at the very precipice of an event horizon. If one of these virtual particles appears just on the edge, its partner might fall across the boundary into the black hole's grip. The doomed particle carries negative energy with it, and in a cosmic sleight of hand, this act of sacrifice allows its partner to become real, escaping into space as a genuine particle of radiation. From the outside, it looks as if the black hole itself is glowing, emitting a faint thermal heat. This Hawking radiation carries energy away, which means the black hole must pay for it by slowly losing mass. Over eons, a black hole can evaporate completely, fading away into nothing but a final burst of particles. This is a breathtaking bridge between worlds, a quantum process that directly dictates the ultimate fate of a gravitational giant. Yet this elegant solution creates a devastating problem. The radiation Hawking predicted is purely thermal, like the heat from a stove. It carries no information, no fingerprint of the stars, planets, or atoms that fell in. If the black hole evaporates, all the information about what it consumed is seemingly erased from the universe forever. This violates a sacred principle of quantum mechanics, the law of unitarity, which states that information can never be truly lost, only scrambled. You cannot burn a book and make its words unrecoverable in principle. This is the core of the black hole information paradox, a direct contradiction that physicist Leonard Susskind argues forces us to rethink the very nature of reality. It suggests that our ideas about where things are located or how quantum states evolve must be fundamentally wrong. The existence of Hawking radiation is a profound clue that information, space, and time are woven together in a way we do not yet understand. hinting that the geometry of the cosmos itself might be built from something more fundamental, a code written in quantum bits. If information cannot be destroyed, then where is it stored when matter falls into a black hole? The holographic principle offers a breathtakingly strange answer. It proposes that all the information needed to describe everything within a three-dimensional volume, every star, every planet, every person, is not contained within that volume at all. Instead, it is perfectly encoded on a two-dimensional surface that surrounds it, like the event horizon of a black hole. Our vivid, three-dimensional reality, in this view, might be a magnificent illusion, a holographic projection from a vast cosmic film stored at the boundary of space. This is not science fiction, it is a serious theoretical framework that emerged from the fiery logic of black hole thermodynamics. The entropy, or the hidden information content of a black hole, was found to be proportional not to its volume, but to the surface area of its event horizon. This was a profound clue that the ultimate description of a region of space might be painted onto its surface, not filled within its depth. The theoretical physicist Juan Maldacena provided a monumental breakthrough with his discovery of the ADS/CFT correspondence. This is a precise mathematical dictionary that links two seemingly unrelated worlds. On one side is a universe with gravity, a bulk space that obeys the laws of general relativity. On the other side is a quantum field theory, a description of particles and forces without gravity that lives on the lower dimensional boundary enclosing that universe. According to this correspondence, these two theories are completely equivalent. They are two different descriptions of the same underlying reality. A complex gravitational event warping space-time deep inside the bulk is exactly the same as a complicated quantum interaction playing out on the boundary. This implies that space-time and gravity themselves may not be fundamental ingredients of the cosmos. They could be emergent phenomena, side effects that arise from a vast, entangled network of quantum information processing happening on a distant, lower-dimensional surface. Think of it like a highly advanced computer simulation. The rich, three-dimensional world you experience in a virtual reality game is not actually built inside your computer. It is generated on the fly from a two-dimensional code, from the ones and zeros etched onto the surface of a silicon chip. The holographic principle suggests our universe might operate on a similar, though far more profound, principle. The solidity of the world around you, the very distance between stars, could be a computational output. This radical idea provides a potential path to finally unify gravity with quantum mechanics. It redefines the conflict not as a battle between two forces, but as a translation problem between two languages, one describing a gravitational reality and the other describing a quantum source code. The very dimensions we move through may just be a convenient, albeit deeply convincing, illusion. But what if the cosmic fabric could be folded? Wormholes, often called Einstein-Rosen bridges, present this tantalizing possibility, a theoretical tunnel creating a cosmic shortcut between two distant points in space-time. These are not science fiction inventions, they are valid, if exotic, solutions to Einstein's own equations of general relativity. The mathematics allows for a bridge or a throat to connect two separate regions of the universe, potentially reducing a journey of billions of light years to a single, manageable step. Yet this incredible shortcut comes with a profound catch. The gateway is catastrophically unstable. The moment it forms, the tunnel would snap shut faster than the speed of light, crushing any hopeful traveler into oblivion. To make such a bridge traversable, you would need a miraculous substance to prop the throat open, something that could exert a negative pressure, effectively pushing the walls of the tunnel apart against the immense force of gravity. This hypothetical substance is known as exotic matter. While it sounds entirely fictional, quantum mechanics does not entirely rule it out. We see a whisper of its behavior in the Casimir effect, where two metal plates in a vacuum are pushed together by the subtle pressure of virtual particles flickering in and out of existence around them. The space between the plates has a slightly lower energy density than the space outside, a fleeting glimpse of the negative energy required. But scaling this quantum quirk to the monumental proportions needed to hold open a wormhole remains firmly in the realm of speculation. This is where the plot thickens, connecting the vast geometry of space-time to the spooky connections of the quantum world. The theoretical physicists Juan Maldacena and Leonard Susskind proposed a revolutionary idea, often summarized as ER equals EPR. They suggested that the mysterious phenomenon of quantum entanglement, where two particles instantly influence each other regardless of distance, might be physically explained by microscopic wormholes connecting them. In this view, what we perceive as a spooky, non-local connection across space is actually a geometric bridge, a tiny, invisible thread woven into the fabric of reality itself. This profound link suggests that the universe's most fundamental correlations are written in the language of space-time geometry. Wormholes are far more than just potential shortcuts. They are extreme thought experiments that stretch the classical rules of gravity to their absolute breaking point. They force us to confront the fact that any real, stable wormhole cannot exist within general relativity alone. It demands the strange, counterintuitive effects of the quantum realm to become physically plausible. They are a perfect symbol of the fusion we seek, a place where the large-scale structure of the cosmos and the tiny, frantic world of quantum physics become one and the same. Einstein called it spooky action at a distance. He was deeply troubled by the implications of quantum entanglement, where two particles once linked seem to communicate instantly across any separation. Imagine two coins, each spinning randomly. Now, imagine that no matter if they are in the same room or on opposite sides of the galaxy, the moment you see one land on heads, you know with absolute certainty the other has landed on tails. This is not a thought experiment, it is a confirmed fact of nature. This instantaneous connection appears to shatter the classical principle of locality, the idea that objects can only be influenced by their immediate surroundings, and that no information can travel faster than light. Yet, the universe does not allow for faster-than-light communication through this mechanism. You cannot use it to send a message. The spookiness is not a bug, it is a feature of reality. This forces a radical reinterpretation of what space actually is. Perhaps entanglement is not a signal traveling through space, but a fundamental property that defines the geometry of space-time itself. Think of the fabric of the cosmos not as a blank stage, but as a vast, intricate tapestry. Each thread in this tapestry represents a quantum connection, an entanglement between particles. Where the weaving is dense and tightly connected, we experience that region as being close, as having proximity. Where the threads are sparse, that translates to vast distances. In this emerging view, championed by physicists like Brian Swingle, space is not a pre-existing container, it is an emergent property of an underlying quantum network. More entanglement literally creates more connectivity, which we perceive as the familiar dimensions of our world. This turns our entire understanding of physics on its head. Instead of space-time being the static stage upon which the quantum drama plays out, the stage itself is built from the drama. The spooky action Einstein rejected may be the very thread that stitches together the quantum and gravitational worlds, weaving the smooth, continuous fabric of general relativity from countless frantic, probabilistic connections. So if entanglement weaves the fabric of space, what does it say about the thread of time? the problem of time presents an even deeper mystery, challenging the very flow of our existence. In Einstein's universe, time is a flexible dimension woven inseparably with space into a four-dimensional fabric. A clock ticks slower near a massive planet, and an astronaut traveling at near light speed ages less than her twin on Earth. Time is dynamic, it stretches and warps, but when we peer into the fundamental equations of quantum mechanics, time is treated as a mere background parameter, an external stage manager that never changes. This creates a profound disconnect when we try to forge a theory of quantum gravity. The resulting equations, like the Wheeler-DeWitt equation, describe a universe without time at all. The variable for time simply cancels out, leaving us with a static picture of reality. It is as if the entire cosmic movie is already complete, with every frame from the Big Bang to the distant future existing simultaneously. We are not watching the film unfold, we are simply tracing a path through the finished reel, experiencing one frame at a time as a persistent, powerful illusion. This is the block universe idea, where the past, present, and future are all equally real. Your birth, your life, and your eventual death are all fixed points in an immense, unchanging four-dimensional structure. The feeling of a flowing now, of moments slipping from future to past, is just a trick of consciousness. This is not just a philosophical curiosity, it is a central obstacle to understanding the Big Bang. At that initial moment when the universe was compressed into a single point, our classical concept of time breaks down completely. To describe the origin of everything, we may need a theory that does not rely on time as a fundamental ingredient. The relentless tick of the clock, the very heartbeat of our reality, might be the grandest illusion of all, emerging from a timeless, deeper layer of quantum information. The ultimate test of this quantum gravity puzzle lies in the very birth of our universe. The Big Bang was not an explosion in space, but the violent emergence of space and time themselves. For a fleeting, impossible moment, the entire cosmos was compressed into a state of infinite density and temperature, a singularity identical to the heart of a black hole. In that initial state, the smooth predictions of general relativity shatter completely. The equations fail, yielding the same nonsensical infinities that haunt the center of a black hole. This was a place where the very concepts of a where and a when lost all meaning. There was no space for anything to exist in, and no time for anything to happen. The question of what occurred at the Big Bang is as meaningless as asking what is north of the North Pole. Our physics hits a hard, impenetrable wall. To peer beyond this wall, we need a theory that can blend the quantum with the gravitational, a framework for a universe where time is not a background tick but a quantum property itself. Cosmologist Alan Guth proposed a pivotal idea to describe the universe's first moments, a theory called cosmic inflation. He suggested that immediately after the Planck time, a strange, repulsive form of energy caused the fabric of space to expand at an exponential rate, far faster than the speed of light. In a fraction of a second, a subatomic speck of primordial reality was stretched to a size larger than our observable universe today. This inflationary surge effectively ironed out any wrinkles, explaining why our cosmos appears so remarkably flat and uniform on large scales. Yet for all its explanatory power, inflation is a description of what happened just after the beginning. It cleverly sidesteps the initial singularity without actually explaining it. The moment of creation, the true genesis from nothing, remains the most profound enigma in all of science. The Big Bang is not an answer, it is the ultimate question. It forces us to confront the possibility that our universe may not have a single, neat beginning in the classical sense, but perhaps emerged from a quantum fluctuation in a deeper, timeless reality, or from a cyclical collision of higher dimensional brains. What came before the Big Bang may be a question without an answer, or it may be the wrong question altogether, one that only a complete theory of quantum gravity can finally reframe. The universe, in its first sliver of existence, underwent a growth spurt of unimaginable ferocity. This was cosmic inflation, a period of exponential expansion that saw space itself stretch faster than the speed of light. In less than a trillionth of a second, a subatomic speck of reality was blown up to a size larger than our entire observable cosmos today. This incredible surge solved profound puzzles. It explains why the universe appears so remarkably flat and uniform in every direction we look, because any initial lumps or curvatures were effectively ironed out by this ultra-rapid smoothing process. But inflation did more than just flatten the cosmos. It also provided a powerful magnifying glass for the quantum world. The seething quantum foam, that chaotic frenzy of microscopic space-time, was suddenly caught in the cosmic expansion. Tiny quantum fluctuations, mere ripples in the energy fields that filled the infant universe, were stretched to astronomical proportions. Think of a tiny wrinkle on the surface of a fully deflated balloon. As you blow up the balloon to an enormous size, that minuscule wrinkle becomes a vast, continent-sized feature. Inflation did exactly this to the fabric of space-time itself. These amplified ripples created regions of slightly higher and lower density, the gravitational seeds for everything that was to come. Over billions of years, gravity pulled on these slightly denser spots, drawing in more and more matter until they coalesced into the first stars, the first galaxies, and eventually the planets. The evidence for this quantum origin story is written across the sky. We can see it in the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light shows tiny temperature variations, a direct imprint of those primordial density fluctuations. The grand tapestry of the cosmos, with its glittering galaxies and vast voids, was woven from the tiniest threads of quantum uncertainty. The driving engine behind this hyper-expansion is thought to be a hypothetical field called the inflaton. This field possessed a unique property, a kind of repulsive gravity that pushed space apart. Yet the exact nature of this inflaton field remains one of cosmology's greatest mysteries. Was it a fundamental force, a new particle, or something else entirely? The fact that a quantum process on the smallest possible scale could dictate the fate of the largest structures we see is a stunning demonstration that the quantum and the cosmic are inextricably linked, two sides of the same reality. Just as we decipher the universe's quantum origins, a far stranger force is reshaping its ultimate fate. Two teams of astronomers, observing distant supernova in the late 1990s, made a discovery so shocking it won the Nobel Prize. They confirmed the universe is not merely expanding, it is accelerating. Galaxies are fleeing from one another at a pace that grows faster with every passing moment, as if an invisible repulsive force is actively stretching the cosmic fabric. This mysterious driver, which we call dark energy, constitutes about 68% of everything in the cosmos. The simplest explanation, proposed by Einstein himself and then famously rejected as his greatest blunder, is the cosmological constant, an intrinsic energy woven into the very vacuum of space. Empty space, according to quantum theory, is not truly empty. It is a seething, bubbling sea of virtual particles, a quantum foam brimming with energy. This vacuum energy should, in principle, exert a gravitational effect. The problem is one of catastrophic scale. When physicists perform the calculations to determine the strength of this vacuum energy, the result is a number so absurdly large it defies reason. The predicted value is 10 to the power of 120 times greater than the amount of dark energy we actually observe. This is not a small error. It is the single worst prediction in the entire history of science. A discrepancy of 120 orders of magnitude is like calculating the mass of a single proton and getting an answer larger than the entire observable universe. This vacuum catastrophe is not a minor puzzle. It is a screaming alarm that our most fundamental understanding of how gravity interacts with the quantum world is profoundly, fundamentally broken. The smooth, continuous space-time of general relativity and the frantic energy of the quantum vacuum are speaking entirely different languages, and their conversation about the energy of nothing has produced a result of monstrous proportions. Dark energy might not be a simple cosmological constant after all. It could be the signature of a new dynamic force field that permeates the cosmos, one that has evolved over time. Or, more radically, it could be a sign that Einstein's theory of gravity, while brilliant, is only an approximation that fails on the very largest scales of the universe. This mysterious pressure pushing galaxies apart forces us to confront a humbling truth. The dominant component of our reality, the very force driving the cosmic expansion, is a complete and total enigma, highlighting a critical fracture in our models of physics. Yet another invisible hand is shaping the cosmos, one that holds the very galaxies together. When astronomers measure how fast stars orbit the center of a spiral galaxy, they expect to see a familiar pattern. The stars on the outer edges, far from the central bulge, should be moving slower than those closer in, just as Pluto orbits our Sun more sluggishly than Earth. But the data reveals something astonishing. Stars on the galactic fringe whip around at nearly the same high speed as those near the center. This is like a cosmic carousel where every horse, whether on the inner or outer ring, spins at the same relentless pace. The visible mass of the galaxy, all its stars and glowing gas, is simply not enough to generate the gravity required to keep these fast-moving outer stars from flying off into the void. Something else must be there, an immense, unseen mass whose gravity creates a stronger grip. This same ghostly presence is felt in the motions of entire galaxy clusters, where individual galaxies move so quickly that the cluster should have torn itself apart long ago unless it was anchored by a tremendous amount of invisible matter. This missing mass is what we call dark matter. It is a substance that does not interact with light in any way. It does not glow, it does not cast a shadow, and it does not absorb or reflect radiation. We cannot see it, but we can feel its gravitational pull as clearly as we feel the sun's warmth. It forms a vast, spherical halo around every galaxy, a cosmic scaffolding that provides the necessary gravitational framework for the luminous matter to cling to. Without this dark skeleton, galaxies like our own Milky Way would have never formed and would quickly disintegrate. So what is this mysterious stuff? The leading hypothesis points to a completely new kind of fundamental particle, one that does not fit into our standard model. These particles are imagined to be massive but incredibly shy, barely interacting with normal matter. They are known as WIMPs, or weakly interacting massive particles. They would flood the universe, passing through our planet and our bodies by the trillions every second without a trace. For decades, physicists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the faint, rare ping of a WIMP colliding with an atomic nucleus. So far, the silence from these experiments has been deafening. This lack of evidence has led other scientists to propose a radically different solution. Perhaps there is no missing matter at all. Instead, our understanding of gravity itself could be wrong on the vast scales of galaxies. This idea, called modified Newtonian dynamics, or MOND, suggests that the force of gravity behaves differently when it becomes extremely weak, as it is in the outskirts of galaxies. It would mean that Einstein's theory of general relativity, while perfect in our solar system, requires a tweak to explain the motions of stars. This is a profound philosophical divide. Is the universe filled with a hidden substance we cannot see, or are the laws of physics as we know them simply incomplete? The search for an answer is one of the greatest detective stories in modern science, involving deep space telescopes mapping the distribution of this dark mass by how it bends light, and powerful particle colliders trying to create it from pure energy. The existence of dark matter is a glaring clue that our map of reality is missing a continent. It tells us that the ordinary atoms making up stars, planets, and us represent less than a fifth of all the matter that actually exists. The rest is a shadow universe, a vast and hidden architecture whose discovery will forever change our place in the cosmos. Even the quantum foam must eventually give way to the solid world we touch and see. But how does this transition happen? This is the measurement problem, the deepest chasm in our understanding of quantum reality. The theory gives us a perfect mathematical description of a particle as a wave of probability, a shimmering cloud of maybes existing in a superposition of many states at once. An electron spins both clockwise and counterclockwise. A photon travels every possible path. Yet, the moment we look, the moment we set up a detector to measure it, this cloud of possibilities instantly collapses. The particle snaps into a single, definite location, a single, definite state, as if it had chosen one reality from an infinite menu. This sudden jump from the possible to the actual is the wave function collapse, and it is the most baffling procedure in all of science. What exactly triggers this collapse? What qualifies as a measurement? Is it the physical interaction with a measuring device, a camera, or a Geiger counter? But these devices are themselves just vast collections of quantum particles, so why should their interaction be special? This line of thinking leads to an even more startling proposition, the idea that consciousness itself is the ultimate catalyst. The Copenhagen interpretation, championed by Niels Bohr, suggests that the observer plays a privileged role. In this view, reality remains an unactualized potential until a conscious mind observes it, forcing the universe to make a choice. This places human awareness at the center of the cosmic machinery, a profoundly unsettling idea that many physicists find difficult to swallow. In stark opposition stands the many worlds interpretation. It offers a breathtakingly bold escape from the paradox. It states that the wave function never actually collapses. Instead, at the moment of measurement, the entire universe splits into multiple, equally real branches. In one branch, you see the electron here, and a new version of you in a parallel world sees it there. Every quantum possibility is realized in its own separate, non-communicating reality. The cosmos becomes an endlessly dividing tree of alternate histories, a multiverse of staggering proportions. Yet this interpretation has its own cost, an infinite proliferation of unseen worlds. The puzzle becomes even more entangled when we bring gravity into the picture. Could the gravitational field itself be the missing ingredient? Some theories, like gravitational decoherence, propose that the sheer act of a particle being in two places at once creates a subtle difference in the curvature of space-time. This gravitational disturbance then acts as a natural measurement, forcing the superposition to collapse into a single classical state. In this view, gravity is not just a force, but the great enforcer of reality, the mechanism that turns quantum possibility into classical fact. The measurement problem is not some abstract philosophical debate. It is the essential, unresolved question of how our definite, intangible world of tables, chairs, and planets emerges from the fuzzy, probabilistic quantum realm. It asks us what it truly means to observe, to measure, and to be, and until we solve it, we cannot claim to fully understand the nature of reality itself. While the holographic principle redraws reality in 2 dimensions, another theory builds the cosmos from the ground up, one tiny loop at a time. Loop quantum gravity proposes that space itself is not a smooth, continuous fabric, but is instead woven from an incredibly dense web of indivisible threads. These are not loops of string, but one-dimensional excitations of the gravitational field, the fundamental quanta of space. Picture a magnificent cosmic tapestry, but instead of soft cloth, it is knitted from countless, interconnected loops of energy. This is the spin network, the underlying structure of reality in this theory. Every single place where these loops intersect represents the smallest possible volume of space, a discrete grain of reality. In this view, you cannot have half a unit of space, just as you cannot have half a photon of light. Area and volume are quantized, coming in tiny, precise packets. This granular nature of space provides a stunning solution to the problem of singularities. The theory's equations show that matter cannot be crushed into an infinitely dense point. Instead, as space is compressed, a tremendous repulsive force emerges from the quantum nature of gravity itself. This leads to a profound reimagining of our cosmic origins. The Big Bang was not the absolute beginning from nothing, but a big bounce, a monumental rebound from a previous universe that had collapsed. Our entire cosmos could be one phase in an endless, cyclical dance of expansion and contraction. Yet this elegant picture is not without its own puzzles. How does this frenetic, discrete web of loops smooth itself out to perfectly mimic the continuous space-time we observe across galaxies? And while the theory gives us a new view inside a black hole, replacing the singularity with a bridge to another region of space-time, the full picture of what happens there remains an active frontier. Loop quantum gravity is a radical departure, suggesting that geometry is not the stage, but the very performance, an emergent property of a universe built from countless interconnected quantum relationships. But what if the most fundamental layer of reality is not made of grains or pixels, but of music? The universe could be a symphony played on unimaginably tiny instruments. This is the radical vision of string theory, which proposes that the ultimate building blocks of everything are not zero-dimensional points, but one-dimensional loops, vibrating strings. Each string is fantastically small, with a length near the Planck scale, and just like a violin string can vibrate at different frequencies to produce distinct musical notes, a fundamental string vibrates in different patterns to create different particles. One specific resonance might manifest as an electron, another as a quark, and another could even be the graviton, the hypothetical quantum particle that carries the force of gravity. This is the theory's most compelling promise, a natural and elegant way to weave gravity into the quantum framework for the very first time. To achieve this mathematical harmony, however, string theory demands a grander stage. The equations only work if the universe has more than the 3 spatial dimensions we know. The theory typically requires 10 or even 11 dimensions for its consistency. So where are these extra dimensions? The idea is that they are compactified, curled up into a space so incredibly tiny, on the order of the Planck length, that they are completely hidden from our everyday perception. Imagine a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to an ant's perspective, you would discover that the hose has a second dimension, a circular cross-section curled tightly around its long axis. Our universe might be analogous, with 6 or 7 extra spatial dimensions coiled into an intricate, complex shape at every single point in space. The specific geometry of this hidden space would then determine the vibrational patterns of the strings, which in turn dictates the laws of physics we observe, from the mass of an electron to the strength of gravity. This leads to a staggering implication known as the string theory landscape. There may be a colossal number, perhaps 10 to the power of 500, of different ways to curl up these extra dimensions. Each unique configuration corresponds to a different possible universe with its own distinct set of physical constants and laws. Our cosmos, with its specific particle properties and forces, would then be just one possible island in a vast ocean of potential realities, a multiverse of incomprehensible variety. This top-down approach suggests that everything we see, all particles and forces, are emergent phenomena, secondary consequences of the underlying geometry of these hidden dimensions. For all its mathematical beauty and ambition, string theory faces a formidable challenge. Critics point out that it has yet to make a single testable prediction that can be verified in a laboratory. The energy scales required to probe these tiny strings or uncurl the extra dimensions are far beyond the reach of any particle collider we could ever build. This leads to the charge that the theory may not be falsifiable, a core requirement for a scientific idea. Yet, even its critics acknowledge the profound intellectual treasures it has unearthed. The holographic principle and the AD/CFT correspondence, which suggests a deep equivalence between a gravitational universe and a quantum theory on its boundary, were direct offspring of string theory research. It has expanded our conception of what is mathematically possible, forcing us to ask if the universe is ultimately built not from stuff, but from the resonant vibrations of cosmic strings. While one theory weaves space from loops of energy, another builds it from the ground up, using the simplest shapes imaginable. This is causal dynamical triangulations, a radical approach that constructs the entire cosmos from tiny triangular building blocks. Forget a smooth, pre-existing fabric. Here, space-time itself is assembled from an enormous number of these fundamental geometric pieces. Think of it like a child's toy set, where you have a colossal bucket of triangular Lego bricks. Each brick represents a tiny, indivisible chunk of space-time. The goal of the theory is to discover what kind of large-scale universe emerges when you connect all these pieces together in every possible way. But there is one crucial rule, a strict condition of causality. Every connection between these triangles must respect a clear arrow of time. In this cosmic Lego set, you cannot build a structure where the future influences the past. Each connection must maintain a consistent and unambiguous distinction between what comes before and what comes after. This causal rule is the secret ingredient that prevents the simulation from collapsing into a chaotic, meaningless foam. When physicists run immense computer simulations, summing over every possible way to connect these causal triangles, something remarkable happens. From a seemingly random jumble of geometric pieces, a smooth, four-dimensional universe spontaneously emerges. It is as if you tossed a billion triangular tiles into the air, and they fell to the ground assembled into a perfect, expansive landscape. This process, known as dimensional reduction, shows how the familiar, continuous space-time of general relativity can arise from a discrete quantum foundation. We experience 4 dimensions, 3 of space and 1 of time, not because they are fundamental, but because that is the stable, large-scale geometry that naturally crystallizes from the quantum connections. This provides a powerful, computational answer to one of the deepest questions. How does the classical world of smooth curves and definite paths solidify from the frantic quantum dance? CDT does not just describe this emergence, it allows us to watch it happen on a screen. the simulations reveal that space-time can undergo phase transitions, much like water freezing into ice or boiling into steam. By adjusting the parameters, physicists can explore a universe where space-time shatters into a disordered, fractal mess, or one where it crystallizes into the four-dimensional continuum we call home. This framework offers a stunningly concrete vision of the universe's birth. In the CDT picture, the Big Bang may not have been a singular, infinitely dense point, but a profound phase transition where space-time itself changed its state, emerging from a more primitive, quantum geometric form. It is a bottom-up revelation, showing us that the vast cosmic stage is not a given, but a magnificent and stable pattern that arises from the humblest of parts. This peaceful image of a smooth passage into a black hole is now under fire. A terrifying new paradox suggests the event horizon is not a placid gateway, but a blazing wall of death. This is the Firewall Paradox, a thought experiment that sets three fundamental pillars of physics against each other. The first pillar is Einstein's cherished equivalence principle, which guarantees that an astronaut crossing the horizon would feel nothing special, no sudden jolt, just the serene fall of free float. The second pillar is the unitarity of quantum mechanics, the sacred rule that information can never be destroyed. The third is the proven framework of quantum field theory, which works perfectly in gently curved space-time and predicts the existence of Hawking radiation. The paradox, crafted by physicists Olmary, Marolf, Polchinski, and Sully, reveals you cannot have all three at once. To preserve the purity of quantum information and make Hawking radiation work, a brutal sacrifice seems necessary. The smooth horizon must go. If information is to escape the black hole via radiation, then the particles just outside the horizon must be deeply entangled with the radiation that has already flown far away. But for the astronaut falling in, quantum mechanics also demands that the particles he encounters right before crossing must be entangled with the particles just inside the horizon. A fundamental rule of quantum entanglement, called monogamy, states that one particle cannot be fully entangled with two different systems at the same time. It is the ultimate quantum love triangle. To resolve this conflict, the entanglement must be violently severed. This breaking of the quantum link releases an astronomical amount of energy, transforming the horizon into a searing curtain of high-energy particles. An astronaut would not float through, they would be instantly vaporized. This firewall forces an impossible choice. Do we abandon Einstein's principle and accept that the horizon is a physical, fiery boundary? Do we let quantum information be lost after all, overthrowing a core tenet of modern physics? Or do we question our very understanding of how quantum fields behave in this extreme gravity? The debate has split the physics community. Some propose that the concept of locality, the idea that things only affect their immediate neighbors, breaks down completely. Others suggest a more radical idea that black holes do not have an interior at all, at least not in the way we imagine. The firewall is more than a puzzle, it is a crisis point. It tells us that our comfortable assumptions about space, time, and information are fundamentally incompatible when pushed to the absolute limit. The event horizon is no longer just a point of no return. It is the front line in a battle to rewrite the laws of physics. This geometric shape, known as the amplituhedron, offers a radical escape from the paradoxes of space and time. It is a pristine, multi-dimensional object whose volume directly encodes the outcomes of particle collisions. For decades, physicists calculated the probabilities of what happens when particles smash together using a method invented by Richard Feynman. This involved drawing and adding up thousands upon thousands of intricate diagrams, each representing a different possible path for virtual particles to flicker in and out of existence. The process was notoriously complex and inelegant, a mathematical maze through the frantic quantum foam. The amplituhedron cuts through this chaos with breathtaking simplicity. The tangled web of Feynman diagrams, with their endless virtual particles and quantum uncertainties, is replaced by a single, beautiful geometric form. The probability of a specific scattering event is simply proportional to the volume of this shape. Perhaps the most profound aspect of this calculation is what it leaves out. The entire procedure is local and unitary by construction, meaning it naturally preserves the core quantum rules of cause and effect and information conservation. Yet it achieves this without ever referencing spacetime or quantum uncertainty as fundamental ingredients. Locality and unitarity are not assumptions fed into the calculation, they are properties that emerge from the geometry itself. This turns our entire understanding of physics inside out. It suggests that the space-time stage and the quantum probabilities playing out upon it are not the bedrock of reality. They are secondary effects, shadows cast by a deeper, more fundamental geometric truth that exists beyond our familiar notions of here and there, or before and after. The amplituhedron formalism has been called the end of space-time because it provides a complete, self-contained description of particle interactions that simply does not need a space-time continuum to function. While this geometric approach is currently perfected for a specific class of theories, its implications ripple across all of fundamental physics. It dares us to consider that our universe is not built from tiny vibrating strings or loops of energy, but from the timeless, perfect relations of pure geometry. The frantic quantum dance and the smooth gravitational curves we experience may just be a clumsy translation of a far more elegant and silent mathematical reality. Our universe's specific laws might be a cosmic accident, a single roll of the dice in a casino with an infinite number of tables. This is the multiverse hypothesis, the staggering idea that our entire cosmos is just one bubble in a vast, frothing sea of realities. This concept does not come from science fiction. It emerges naturally from the edges of our most ambitious physical theories. The same cosmic inflation that flattened our universe and seeded its galaxies could be an endless process, with different regions of space stopping their hyper-expansion at different times, each one cooling into a separate universe with its own unique properties. String theory deepens this picture with its landscape of possibilities. Recall those tiny, curled-up extra dimensions, their specific geometry dictating the laws of physics. There are an astronomical number of ways for them to fold, perhaps 10 to the power of 500 distinct configurations. Each one corresponds to a different vacuum state, a unique set of physical constants. In one universe, the strength of gravity might be a crushing force, preventing stars from ever forming. In another, the nuclear forces could be too weak to bind protons and neutrons, leaving only a featureless sea of hydrogen. Our universe, with its specific masses and forces, is simply one point in this colossal landscape, a single bubble that inflated with a particular, life-friendly set of rules. This perspective offers a potential solution to the puzzle of fine-tuning. Why do the fundamental constants seem so perfectly calibrated to allow for atoms, stars, planets, and life? If there is only one universe, this seems like a miracle. But if there is a multiverse, then it is no surprise we find ourselves in one of the rare bubbles where the numbers just happen to work out. This is the Entropic Principle, the idea that our observations are biased by the necessity that we exist to make them. We do not see a universe hostile to life because we could not be here to see it. Yet this very explanatory power is the source of the multiverse's deep controversy. If other universes are permanently beyond our horizon, causally disconnected from us forever, how can we ever test their existence? Critics argue that a theory that can explain anything by invoking an infinity of unseen worlds risks explaining nothing at all. It pushes the very definition of science to its limit, forcing us to ask whether a hypothesis must be directly falsifiable to be considered scientific, or if its explanatory power within a larger theoretical framework is enough. The multiverse stands as the ultimate expression of broken symmetry, a place where the fundamental laws of physics themselves are not laws at all, but local bylaws varying from one cosmic island to the next in an ocean of infinite possibility. The search for quantum gravity is stepping out of the black hole and into the laboratory. Believe it or not, we may not need a particle accelerator the size of a galaxy to test these cosmic ideas. Scientists are now designing ingenious tabletop experiments to catch the first whispers of gravity's quantum nature. One audacious approach uses supercooled, microscopic oscillators, tiny vibrating paddles chilled to near absolute zero. At this frigid state, their motion is so quiet that researchers hope to detect if it's subtly jostled by the seething quantum foam of space-time itself. It is like trying to measure how the frantic bubbling of a carbonated drink makes a single ice cube tremble. Another line of inquiry hunts for hidden dimensions and granular space by testing gravity's most trusted rule at vanishingly small scales. For centuries, we have known that gravity weakens with the square of the distance, a principle called the inverse square law. But if space is woven from discrete loops or if extra dimensions are curled up tightly, this law should break down when two masses are brought incredibly close together. Finding even a tiny deviation would be like discovering a secret door in a room you thought you knew perfectly. Perhaps the most profound of these experiments involves entanglement. By trying to entangle two tiny but massive objects like microscopic diamonds, physicists are asking a fundamental question. If the diamonds become linked, will their own gravitational interaction, however faint, be enough to destroy that delicate quantum connection? A positive result would suggest that gravity itself is the great enforcer, the mechanism that inevitably turns fuzzy quantum possibility into definite classical reality. Of course, these experiments are feats of extreme precision, requiring near-perfect isolation from every vibration, every whisper of heat, every stray electromagnetic wave. They are attempts to hear a single note in a cosmic symphony while standing in the middle of a hurricane. Yet their promise is immeasurable. A single positive result from any one of these lab benches would shatter our current understanding, gifting us the first direct evidence of how gravity truly behaves in the quantum realm. These are not just experiments, they are our most tangible bridge from the abstract equations of theoretical physics to the concrete, testable laws of our universe. But who is the observer that forces reality to choose? The measurement problem thrusts consciousness itself onto the stage of fundamental physics, a deeply controversial player in the quantum drama. Some of the 20th century's greatest minds, including John von Neumann and Eugene Wigner, proposed a startling solution that the wave function collapses only when it interacts with a conscious mind. In this view, the entire universe remains in a shimmering state of potential until an observer, a conscious being, looks at it and forces it to become concrete. This idea places an immense weight on perception, suggesting that the moon is not truly there when no one is looking, its existence dependent on a mind to observe it. It is a proposition that borders on the mystical, making consciousness a fundamental component of reality itself. Yet most physicists today find this interpretation deeply unsatisfying. They point to the process of decoherence as a more physical explanation. Decoherence describes how a fragile quantum system, like a spinning electron, inevitably interacts with its surrounding environment, with stray photons and air molecules. This constant bombardment instantly leaks the system's quantum weirdness into the environment, scrambling the delicate superposition. The electron appears to collapse into a definite state, not because a mind observes it, but because it has become inextricably entangled with the vast, noisy world around it. The classical world emerges not from consciousness, but from this relentless interaction. This debate strikes at the heart of the hard problem of consciousness, the question of why and how physical processes in the brain give rise to subjective experience, the feeling of what it is like to be. Does a flawless quantum computer processing information in superpositions need to be conscious to function? Or is it just an exceptionally complex arrangement of atoms, its calculations no more conscious than a falling rock? The question forces us to ask if a complete theory of the universe can ever be truly complete if it has nothing to say about the inner world of the observer, the mind that perceives the cosmos and asks these very questions. Are we passive witnesses to a reality that unfolds independently, or are we, in some strange and fundamental way, participants in its very creation? This remains one of the most speculative and philosophically charged frontiers of all, a place where physics meets the inner mystery of our own awareness. This emptiness of space is a profound illusion. Quantum field theory insists that the vacuum is not a void but a vibrant, chaotic sea. At every single point, virtual particles and antiparticles are constantly boiling into existence, borrowing energy from nothing for the briefest moment before annihilating and vanishing back into the void. These are not mere mathematical quirks, they have real, measurable effects, like the Casimir force pushing metal plates together. When physicists attempt to calculate the total energy of this frantic quantum activity, the result is a number of such staggering magnitude it defies comprehension. This is the predicted value of the cosmological constant, the energy density of empty space itself. If this theoretical number were correct, the sheer vacuum energy would generate a repulsive gravity so powerful it would have ripped every atom, every star, and every galaxy apart in the universe's first instant. The cosmos as we know it would not exist. Yet when astronomers measure the actual expansion rate driven by dark energy, they find a value that is almost zero. The discrepancy is not a small error. It is a catastrophe of 120 orders of magnitude. To grasp this scale, it is the difference between calculating the weight of a single apple and getting an answer heavier than the entire observable universe. This is the cosmological constant problem, the single worst prediction in the entire history of science. Why is the energy of the vacuum so exquisitely fine-tuned to a value that is nearly, but not perfectly, zero? This is not just a minor puzzle, it is a screaming alarm that our understanding of how quantum fields interact with the gravitational fabric of space-time is fundamentally, profoundly broken. One proposed solution lies in a beautiful symmetry called supersymmetry. This theory posits that every known particle has a hidden superpartner. The frenetic energy contributions from ordinary particles could be perfectly cancelled out by the opposite contributions from their supersymmetric twins. It is a cosmic balancing act of perfect precision. The problem is, we have not found any of these superpartner particles in our most powerful colliders, suggesting that if supersymmetry exists, this elegant cancellation is somehow broken in our reality. This leads to an even more radical explanation rooted in the multiverse. In a landscape of infinite universes, each with randomly determined physical constants, the vacuum energy would take on every possible value. In the vast majority of these universes, the cosmological constant would be so enormous that no structures could ever form. We, of course, find ourselves in one of the exceptionally rare bubbles where the vacuum energy is minuscule enough to allow for galaxies, stars, and life to evolve. Our existence as observers automatically selects for this incredible fine-tuning. The puzzle of the near-zero vacuum energy is a direct confrontation, forcing a final theory of quantum gravity to explain why the furious activity of the quantum world leaves the cosmic stage so silent and so empty. So where does that leave the book you threw into the black hole? Is its story truly lost forever? The fate of information is the ultimate litmus test for any theory of quantum gravity. Quantum mechanics holds one principle as sacred: information is never destroyed. Burn a book, and in principle, every single letter could be recovered from the precise pattern of the smoke and the ashes. The information is scrambled, but it still exists. Stephen Hawking's original calculation presented a direct challenge to this foundational rule. He argued that a black hole evaporates into a formless, random heat, a thermal radiation that carries no fingerprints, no history, and no information about the stars and planets that built it. If the hole vanishes completely, the information it ever consumed would be erased from our universe. This is the core of the paradox, a direct contradiction that pits the smooth geometry of general relativity against the unbreakable rules of the quantum world. How can both be true? The search for a solution has led to some of the most radical ideas in modern physics. One compelling proposal is black hole complementarity. It suggests that from two different perspectives, two contradictory stories can both be true. From the viewpoint of an astronaut falling in, they cross the event horizon uneventfully, and the information travels with them into the black hole's interior. But from the viewpoint of an outside observer watching from a safe distance, the information never actually crosses the horizon. Instead, it is scrambled and encoded onto the event horizon itself, a vast spherical hard drive, and then slowly radiated back out in the Hawking radiation. Both stories are valid within their own frames of reference, and no single observer can ever see the contradiction. It is as if reality has a built-in censorship rule to prevent logical paradoxes. Another, even more mind-bending idea is that the information does not come out or get stored, but instead escapes into an entirely new region of space-time, a baby universe that pinches off from our own. In this view, a black hole is not a final grave but a cosmic womb. The most recent breakthrough comes from the holographic principle and is known as the island conjecture. It reveals that thanks to the bizarre properties of quantum entanglement, information that seems locked deep inside the black hole can actually be reconstructed from a region far outside the event horizon. This region is called an island. Think of it as a quantum backup drive that appears not within the black hole, but in the space just outside it, connected to the interior through a web of entanglement. An outside observer could, in theory, piece together what fell into the black hole by performing an impossibly complex calculation on this escaping radiation and its entangled island. This forces a complete rethink of what we mean by inside and outside. The very location of information becomes a fuzzy quantum concept. This ongoing debate is about much more than the fate of a few atoms. It strikes at the heart of causality and locality. Can an effect truly be separated from its cause if information can be in two places at once? The black hole information paradox is not just a puzzle. It is a gateway, compelling us to rewrite the rules of reality until the universe's most cherished stories are never truly lost. The stage we thought was permanent might be a temporary mirage. Emergent gravity proposes that space-time is not a fundamental layer of reality, but a collective behavior, an illusion that solidifies from something more basic. Think of the air in a room. You do not feel individual molecules constantly bumping into you. You experience a smooth, continuous pressure. In the same way, the smooth, geometric fabric of space-time could be a kind of average, a large-scale effect that arises from the frantic interactions of countless underlying quantum components. These components might be bits of information or perhaps entangled qubits, their interconnections weaving the very notion of proximity and distance. Physicist Eric Verlin took this idea a step further, suggesting that gravity itself is not a fundamental force, but an entropic one. Entropy is a measure of disorder, the universe's natural tendency to move toward more probable, scrambled states. Verlin's theory posits that gravity is a consequence of this cosmic tendency. When two masses are near each other, the most probable arrangement of the underlying quantum information is one where they are closer together. The force we perceive as gravitational attraction is simply the system evolving toward this higher entropy state. A simple analogy is a tangled polymer, a long, coiled molecule. If you try to pull it straight, it resists. This is not due to a fundamental force of repulsion, but because the polymer has a vast number of tangled, high-entropy states and only a few orderly, straight ones. It naturally springs back to disorder. In this view, the Earth does not pull on the Moon through a mysterious force warping space. The configuration of quantum information simply makes it so that the Moon staying in orbit represents the most statistically likely, highest entropy arrangement. This perspective turns Einstein's genius on its head. His beautiful equations of general relativity, which describe gravity as the curvature of space-time, would not be wrong, but they would be analogous to the equations of thermodynamics. We do not need to track every single air molecule to understand temperature and pressure. We use thermodynamics as an effective, large-scale theory. General relativity would be the thermodynamics of space-time, an incredibly accurate description of the emergent phenomenon, but not the final story of its quantum origins. This radical shift could solve one of astronomy's biggest mysteries, dark matter. Perhaps the strange motions of stars within galaxies are not caused by some invisible, exotic particle. Instead, they could be a signature that our understanding of emergent gravity is incomplete on those vast scales. The extra gravitational grip we attribute to dark matter might just be the universe telling us that the quantum information underlying empty space has a different, more complex entropy than we thought. The stage of space-time is not just a passive backdrop, it is an active, dynamic participant born from a deeper quantum reality. Einstein introduced a fudge factor into his most beautiful equations. He called it the cosmological constant, a mathematical term he inserted to counteract gravity and allow for a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble later discovered that the universe was not static but actually expanding, Einstein famously dismissed his own idea as his greatest blunder. The irony is profound, for this rejected concept has made a stunning comeback. The cosmological constant is now the leading candidate to explain dark energy, the mysterious force accelerating the expansion of the cosmos. That number he tried to throw away now appears to be one of the most important in all of physics. The measured value of this constant is positive, confirming the repulsive force of dark energy, but it is also incredibly, bafflingly small. This is where we hit the fine-tuning problem, a puzzle of cosmic proportions. Our best theories of the quantum vacuum predict a sea of frantic energy, a turmoil that should give the cosmological constant a value 120 orders of magnitude larger than what we observe. That is not a small error. It is like predicting a tsunami and finding only a single, gentle ripple in a pond. Why is the energy of empty space so exquisitely tuned to be nearly zero, yet not perfectly zero? This question sits at the fiery crossroads where quantum field theory collides with general relativity. It is a direct confrontation between the frantic world of the very small and the serene geometry of the very large. Some physicists, particularly within string theory, propose a radical answer. They suggest our universe is just one bubble in a vast multiverse, a landscape of countless realities where the cosmological constant takes on every possible value. We simply find ourselves in one of the rare, life-friendly bubbles where the number is almost zero. This anthropic reasoning is elegant, but it feels like a surrender to some, a way of explaining away a fundamental problem rather than solving it. Others search for a more satisfying, dynamical mechanism within a single universe, a physical process that would naturally drive the constant toward zero. The stakes could not be higher. The value of the cosmological constant does not just explain the present, it dictates the ultimate fate of everything. A constant too large would have torn the universe apart before stars could form. A constant with a different sign could have caused a catastrophic collapse. Our specific, tiny value points toward a future of endless, accelerated expansion, a cold, dark fade into emptiness. This single number is a direct link, a bridge between the furious, unseen quantum vacuum and the vast, visible architecture of the cosmos, and unlocking its secret may be the final key to a complete theory of reality. Look at a broken egg. You will never see its shell piece itself back together, its yolk and white leaping up from the floor to reassemble in a perfect, seamless whole. Our world is filled with these one-way streets, from the way heat disperses to the way memories are made. This is the arrow of time, a fundamental feature of our existence that points relentlessly forward. Yet the fundamental laws of physics, the equations governing particles and forces, are almost perfectly symmetric. They do not care if time runs forward or backward. A video of two planets orbiting could be played in reverse and it would look just as valid. So why does our reality have such a powerful, undeniable direction? The answer appears to lie not in the laws themselves, but in the specific arrangement of the universe. The second law of thermodynamics states that the total entropy, a measure of disorder or randomness in a closed system, always increases. Think of a drop of ink in a glass of water. It will naturally spread out, mixing evenly until the water is uniformly tinted. It will never spontaneously unmix and recoalesce into a single, dense drop. This drive toward higher entropy gives time its arrow. The coffee mixed with cream, the shattered glass, the aging of your own body, all are manifestations of the universe's march toward greater disorder. But this explanation simply pushes the mystery one step further back in time. If entropy always increases, then it must have been lower in the past. This leads us to a stunning conclusion about the origin of everything. The Big Bang must have been a state of extraordinarily low entropy, a condition of almost unimaginable order. The entire observable universe erupted from a hot, dense, and remarkably uniform state. This is the ultimate unsolved puzzle. Why did the universe begin in such a special, highly ordered configuration? Some physicists suggest the arrow of time is tied to the expansion of space itself. As the cosmos stretches, it creates more room for disorder to spread, driving the increase in entropy. Others wonder if the very act of quantum measurement, the collapse of the wave function from possibility to reality, imposes a direction on time. The flow of time may not be a fundamental feature of the cosmos, but an emergent property, a story that unfolds because of a unique and still unexplained starting point. Without this low entropy beginning, cause and effect would blur, history would have no meaning, and the universe as we know it would be an impossible jumble. The direction of time is the silent, invisible river that carries us from a mysterious past toward an uncertain future, and we are only just beginning to understand its source. This profound imbalance between the quantum world's frantic energy and the cosmic stage's silent emptiness demands a solution of exquisite elegance. Supersymmetry offers just that, a theoretical bridge of breathtaking beauty that could connect the two kingdoms of physics. It proposes a deep, hidden symmetry in nature, a partnership where every particle we know has a hidden twin. The universe's particles are divided into two families. Fermions are the building blocks of matter, the quarks and electrons that form atoms and everything in them. Bosons are the force carriers, the photons that bring us light, and the gluons that bind atomic nuclei. Supersymmetry, often called SUSY, suggests that for every fermion there exists a superpartner that is a boson, and for every boson, a superpartner that is a fermion. This would double the number of fundamental particles. The electron, a fermion, would be paired with a theoretical boson called the selectron. The photon, a boson, would be paired with a fermion called the photino. This elegant pairing is more than just a cosmic duplication. It is a potential key to unlocking the universe's greatest puzzles. One of its most vital roles is to stabilize the mass of the Higgs boson. The Higgs gives other particles their mass, but according to quantum field theory, its own mass should be driven to an astronomically high value by interactions with virtual particles. This is the infamous hierarchy problem. The superpartners in SUSY would act as perfect counterweights. The wildly fluctuating contributions from known particles would be precisely cancelled out by the opposite contributions from their supersymmetric twins, naturally keeping the Higgs mass at the delicate, low value we observe. This cosmic balancing act would also provide a perfect candidate for the mysterious dark matter that holds galaxies together. In many SUSY models, the lightest supersymmetric particle, or LSP, is stable and does not interact with light. It would flood the universe, forming vast, invisible halos around galaxies, exactly as astronomers observe. This particle, often thought to be the neutralino, could be the dark matter we have been searching for all along. Furthermore, supersymmetry is a cornerstone of string theory, helping to tame the mathematical infinities that arise when gravity is forced into the quantum framework. By providing this extra symmetry, SUSY makes the equations of quantum gravity behave, offering a path toward that final, unified theory. Yet for all its mathematical harmony and explanatory power, nature has so far kept its superpartners hidden. The Large Hadron Collider, our most powerful microscope, has searched for these particles and found nothing. The simplest, most elegant versions of supersymmetry have been ruled out. This does not mean the idea is dead, but it forces the theory to be more complex, with superpartners that are much heavier and harder to detect than initially hoped. The search continues because the promise of supersymmetry is simply too compelling to abandon. It represents a vision of a deeply connected cosmos, where matter and force are two sides of the same coin, and where the answers to our most profound questions may lie in the shadow of a symmetry we have yet to see. Perhaps the universe is not made of fields or particles, but of information. Every electron's spin, every photon's path, could be a single bit in a cosmic calculation unfolding since the dawn of time. This is the audacious idea of pancomputationalism, which posits that the laws of physics are not just like computational rules. They are the software, and the universe's entire evolution is one vast, ongoing computation. Every interaction, from the fusion in a star's core to the chemical dance in a single cell, is a processing of information. The theoretical physicist Seth Lloyd has championed this view, suggesting we consider the universe itself a quantum computer. In this framework, the cosmos is not merely described by mathematics. It is actively performing a calculation, with every event a logical operation in a program of unimaginable complexity. This perspective finds a stunning home in the quest for quantum gravity. Some approaches propose that space-time geometry does not exist fundamentally, but emerges from a more primitive network of entangled quantum bits or qubits. The three-dimensional world we move through, with its distances and durations, could be a collective output generated by the ceaseless, correlated computations of these fundamental information units. The holographic principle powerfully reinforces this. It tells us that all the information describing a volume of space is encoded on its surrounding boundary, much like the entire three-dimensional world of a virtual reality game is generated from a two-dimensional code on a computer chip. If this is true, then the universe operates on a similar principle, with our reality being a magnificent projection from a cosmic hard drive. This radically reframes our most fundamental quest. The search for a theory of everything is no longer just a hunt for the ultimate particle or force. It becomes a search for the universe's source code, its fundamental algorithm. Finding the unified laws of physics might be equivalent to discovering the universe's operating system, the foundational program that has been running since the Big Bang. This computational lens unifies physics with information theory and computer science, offering a powerful new way to decode cosmic mysteries. It suggests that at its heart, reality may be less about what things are and more about what they do, processing information in an endless, breathtaking computation. The fabric of space-time is not silent. It rings like a bell when massive objects collide, and we have learned to listen. These vibrations are gravitational waves, ripples in the cosmic fabric predicted by Einstein and finally detected by the LIGO and Virgo observatories. When two black holes spiral into each other, they shake the universe, sending out a faint whisper that travels across billions of light years. Our instruments here on Earth have captured this whisper, transforming it into a sound we can hear, a cosmic chirp that marks the most violent events in the cosmos. This discovery did more than confirm a century-old prediction. It handed us an entirely new sense for observing the universe. We are no longer limited to the narrow band of light. We can now feel the very vibrations of reality. These waves provide the ultimate testing ground for general relativity, pushing it to its absolute limit in the strong gravitational fury of a merger. But could they also carry a message from the quantum realm? The final moments of a black hole merger are a storm of unimaginable force, where space and time are contorted beyond recognition. It is precisely in this chaos that the smooth predictions of Einstein's theory might begin to crack, revealing a finer quantum grain. Some theories of quantum gravity suggest that the event horizon is not a perfectly smooth mathematical surface, but has a subtle structure. This quantum fuzz could act like a semi-reflective barrier, causing some gravitational waves to bounce back. The main collision would produce its characteristic chirp, but then, a fraction of a second later, we might detect faint, repeating echoes. These echoes would be the signature of quantum geometry, a direct sonic imprint of a horizon built from discrete bits of information. Finding them would be like hearing your voice reverberate in a room you thought was infinitely vast, suddenly revealing its hidden walls. Beyond these cataclysmic local events, there is a far more ancient hum to listen for. The entire cosmos is filled with a faint, random sea of gravitational waves, a background rumble from the universe's earliest moments. This primordial signal, if we can detect it, is a fossil from the Planck era, a time when the cosmos was so small and energetic that quantum gravity ruled everything. The pattern of this cosmic hum could be imprinted with the distinctive texture of quantum foam or the vibrations of cosmic strings. It would be a recording of creation itself, a direct message from the birth of space and time. As our detectors become more and more sensitive, we are not just confirming Einstein's universe, we are listening for the cracks in it. Every deviation from the perfect chirp, every unexpected echo or statistical anomaly in the background static is a potential clue. Gravitational wave astronomy has handed us a stethoscope to place against the chest of the cosmos, allowing us to listen for the quantum heartbeat of reality. The dream of a final theory, a single set of equations that describes the entire cosmos, has driven physics for generations. We yearn for a perfect unification, a framework where the frantic quantum dance and the smooth curvature of gravity are revealed as two faces of the same coin. Yet this quest for a grand synthesis may be leading us toward something far more disruptive than a mere handshake between old ideas. The very concepts we take for granted, the stage of space and time, could be the very obstacles preventing a deeper understanding. Perhaps the universe is not built on a foundation of geometry at all. The most promising paths forward are already pointing in this radical direction. String theory replaces point-like particles with vibrating loops, but demands a cosmos of 10 or 11 dimensions. Loop quantum gravity weaves space from a fabric of discrete, interlocking threads. Emergent gravity suggests that space-time itself is a collective illusion, a thermodynamic mirage rising from a sea of quantum information. Each of these approaches is a monumental intellectual achievement, yet each faces its own profound challenges, from a lack of experimental evidence to the dizzying complexity of their mathematics. The history of science whispers a cautionary tale. Isaac Newton's clockwork universe seemed absolute until Einstein showed that time was relative. The smooth fabric of general relativity seemed complete until quantum mechanics revealed a seething underworld of probability. Our current crisis feels familiar. The breakthroughs of the future may not come from forcing our existing theories to agree, but from a source we cannot yet anticipate. A single, unexpected signal from a gravitational wave detector, a strange result from a tabletop quantum experiment, or a flash of mathematical genius from a new generation could shatter the paradigm entirely. We may have to let go of locality, the idea that things only influence their immediate neighbors. We may have to accept that time is not fundamental. The resolution to the puzzle of the quantum fabric will not just fill a gap in our textbooks. It will redefine reality as profoundly as the revolutions of the past century, revealing a cosmos stranger and more wonderful than we have ever dared to imagine. This is not the end of physics, but the thrilling beginning of its next great transformation. Our journey has taken us to the precipice of knowledge itself, a place where the solid ground of physics gives way to a quantum frontier. We have stared into the infinite maw of a singularity and felt the chaotic tremor of space-time foam. We have witnessed the elegant dance of general relativity clash with the frantic probability of the quantum world, a conflict that is not a simple error in our math, but a beacon pointing toward a reality far deeper than we have yet conceived. This is not the end of physics, but a magnificent crisis, a necessary breaking of our old models to make way for a new understanding. Whether the final answer lies in vibrating strings, woven loops, a holographic projection, or a principle still waiting to be discovered, one thing is certain. The resolution will not just complete a textbook, it will fundamentally redefine our cosmic story, reshaping our very conception of what it means to exist within this universe. The great physicist John Archibald Wheeler left us with a humbling image. He said we live on an island of knowledge surrounded by a vast sea of ignorance. And as our island grows, so too does the length of its shoreline, the frontier of all we have yet to learn. Let this exploration be your invitation to walk that ever-expanding shore. The cosmos is far stranger, more mysterious, and more beautiful than our classical minds can fathom. We would love to hear which of these profound mysteries captivates you most. Share your thoughts in the comments and subscribe to join us as we continue venturing to the furthest edges of science.